we started with original graphs yesterday, and we shifted them right 5 and kind of came up with a new graph over and over again. What we're going to do today is come up with a new graph as well, but there's multiple transformations. So yesterday I stuck to just one transformation and we worked on shifting the graphs or stretching the graphs. Now there's multiple transformations on the same problem. So it's going to get a tiny bit more complicated just because if you've got multiple transformations, you're going to have multiple graphs if you do a transformation for each individual thing. So for example, this particular one, what's the movement? If you had to describe that. Yep, go ahead. Right 3 up 1. So I'm just going to write that. Okay, now when there's two transformations, I don't think it's necessary to move the graph right 3 and let that be an intermediate stopping point, and then taking all those and moving them up 1. When they're both transformations, it's easy enough just to do it all at once. Take every critical point, so starting with this one here, move it right 3 and up 1. Here's another critical point down here. Move that right 3 and up 1. Here's my next critical point. I'll move this one right 3 up 1. And then my last critical point, which ended my graph, right 3 up 1. And then just straight edge to connect. Your points. Some of them, as we move on, we're going to see it's kind of tough to do all of it at once. But when it's transformations stacked up on each other, that's not a problem. All right, so the original graph was f of x. And the new graph is g of x. So I'm labeling those. Part A asks us, what is the value of g of 0? Now, it wants us to kind of show that it works out both ways, so algebraically and graphically. So let's pretend we haven't graphed g of x yet. We'll do it algebraically first. If you want g of 0, but you pretending we didn't have a graph to look at, nor do we have an equation to really plug it into, well, maybe we do. What you should do is find f of 0 first. So from your graph, f of 0 is -1, -2. You with me there? If f of 0 is -2, is g of 0 going to be that same point shifted right 3 and up 1? Think about that. No, right? F of 0 is -2. We can see, because we do have the graph, that g of 0 isn't that. So instead of doing that, let's do it algebraically and just plug it in. It's not a traditional equation, but watch how this pans out. If I want to do g of 0, I plug in 0 to g of x. So g of 0 equals f of 0 minus 3 plus 1. I'm just plugging 0 into this function, just like I would find g of anything in any other type of equation that's been given to me. Just plug 0 into that equation. So what's that? That's going to create this f of -3 plus 1. And obviously remembering that this is function notation. This is not f times -3. This is function notation, f of -3. Go to your f graph. F of -3 is 1. Are you guys with me there? So that's going to be 1 plus the 1, which will put me at 2. And then sure enough, we'll confirm that graphically. G of 0, if I look on my graph, x coordinate of 0 and 2 units up, there is your point on the G graph. Okay? So just like anything else, if you're asked for g of 0 and you have to find it algebraically, plug it in and see how it pans out, and somewhere in there you're going to have to do f of something and use that graph. Any questions on that? The domain of f of x. We haven't really reviewed domain and range like precisely. We've talked about it, and I've just kind of assumed that you know what the domain and range is. So let's kind of just do a random sample to see if we do. Lucas K. What's the domain of f of x?
It goes from -4 to 3.
From -4, perfect. That's the furthest left f of x is. And then to 3 on the right, perfect. Does that make sense? Domain is kind of the span of the graph left to right along the x-axis. So we're going to write -4 is less than or equal to x is less than or equal to 3. You know what I'm realizing about this graph? Is that the x-axis and the y-axis are not as bold as I would like them to be. So I'm going to do this just so it's easier to read. You can do the same on yours. And then how about the range, Natalie? -2 looks good. 1, 2, 3, 4. Very good. So the range is the span low to high along the y-axis. So -2 is less than or equal to y is less than or equal to 4. In other words, all of your x-coordinates on the f of x graph fall between -4 and 3. All of your y-coordinates fall between -2 and 4. Good-oak? And then, so your domain of g of x and your range of g of x, because we do have the graph in front of us, we could also do it visually, or we could do it like we just did on our homework, right? Where we already know the domain and range of the original. If this was moving right 3, that's going to change our domain right 3 units. So Sierra with an S, what would that look like?
-1 less than or equal to x. It's less than, right?
Yeah. You always go smallest to biggest, so there'll always be less thans.
Okay, less than or equal to 6.
Very good. Okay, so she just added 3 to both because we're moving 3 to the right. And Sierra with a C, how about the range? And which method did you use for that? Did you use the previous range to get there, or did you just look at the graph? She looked at the graph. But if you did use your previous one, remember we were moving up 1, so just take that range and add 1 to both of those. Okie doke? All right. Try exercise 3 on your own. Tess, what do you have for me? What's that? Okay, good. That's what I'm here to uncover. So your domain is your x coordinates, right? And based on this transformation, what is happening to your x coordinates? What transformation? Left 7, very good. So inside is horizontal, it's plus, so it's a transformation, and since it's backwards because it's horizontal rather than being right 7, it's actually left 7. So if you move these numbers, because those are your x's, left 7, what would negative 3 become if it moves left 7? Think about a graph. Here's negative 3. If I move it left 7, 1, 2, 3, 4, 5, 6, 7, it's now going to be here, which is at negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Negative 10. How about if I take positive 10 tests and I move that left 7? So if I'm way out at positive 10 and I go back 7 units to the left, where am I? 3. Is that helpful? Okay. And then the range. What do you think about that, Chloe?
Oh, I have a question.
Oh, yeah, good.
Will the numbers always flip-flop, like 10 switch to negative 10 and 3 switch to negative 3?
No, it just happened to pair that way. I mean, we saw in our homework last night that's not what happened. It didn't happen here either. Okay. It just somehow, with the way that they wrote it, moving negative 3 left 7 happens to put you at a 10, and moving 10 left 7 happens to put you at a 3. They just kind of designed it probably to confuse you. I don't know. Yep.
For the range, like what would be before the 1?
So when a domain or a range is limited on both sides, that means it's always between those two numbers. Something that has a range that's only really limited on one side, just it has to be under 22, probably is some sort of graph that goes down forever and has an arrow at the end of it putting it down infinitely. So it doesn't have a lower bound. So when you move this, what transformation is this, Angie? After the left 7, how is this going to move?
Down.
Not down, up, because it's plus. Yep.
Why would the plus 7 be moved?
Someone help her with that. Why would the plus 7 be left, but the plus 10 is up? Go ahead.
Because it's horizontal and it flips sides. So
Right. This one that's horizontal, everything that's in the horizontal is like backwards. You know what I mean? Like you would think plus 7 would move it to the right, but it moves it to the left. That's because it's horizontal, and horizontal is like weird. Vertical is what you would think it would be. If you think of adding 10, you should think of up 10. Okay, so just horizontal is just misleading. If you remember that and you always go backwards of what your gut would say on horizontal, you'll be good. So it's actually up 10. And so how would that fix your range? Ann? Oh, Ann's not here anymore. Sorry. Alexa. Y is less than or equal to 32. Very good. Okay? It does say explain. I'm not going to write a sentence right now, but you would say something along the lines of, in the transformation, the graph is being shifted left 7, which is going to move all of our domain points down 7. And the transformation vertically is moving everything up 10, so that's going to increase our range by 10. Okay? Write something thorough like that, and we don't have to write it right now, but that's what I would be looking for. Remember, explain always is going to mean a sentence. In 4, okay, 4 is a little bit trickier because it's not just like a generic f of x. It really is, it's piggybacking off of a quadratic function. So your typical parent graph for a quadratic function, and I'm just using g of x because this one used f of x, is just x squared. So if that's your original parent graph, and then here's your transformation, Part A says, how has this one been shifted? Does everyone see, obviously everyone sees the -4 and the -5. So there are two transformations. Can we all, jump on the bandwagon and realize that this -4, this -4, is happening, quote unquote, inside the function? Does that make sense? So because it's kind of within the x squared, that's your horizontal right 4. Shift right 4. And the -5 is after the fact. We go with that? So the -5, given that it's outside of the parent graph main equation, means it's vertical, shift down 5. And then B is much like our homework quiz. Given that y equals x squared has a turning point at the origin, where's the turning point of f of x? So 0, 0, shifted right 4 and down 5 would be where, Bella?
4 negative 5.
4, -5, perfection. Okay? Any questions so far? I think exercise 2 is going to kind of pick it up a notch for some of you who are thinking this is easy. And if you're thinking this is challenging, still, you're not wrong. It is a tough thing to wrap your head around because there's just a lot of transformations going on. But this will definitely kick it up a notch. So this gives us a linear function, g of x. It wants us to come up with an equation after a reflection in the x-axis and the y-axis. So let me be honest with you. The order, if you're doing two reflections, is not going to really matter. But we should always do which reflection first, the horizontal or the vertical, just to stay consistent, because sometimes it will make a difference. So a horizontal reflection first is when you negate it within the function. Okay? So just like we practiced with function notation, if I said to do g of 5, you'd plug in a 5. Well, if I'm saying to do g of negative x, we're going to plug in a negative x. So that's going to be 5 times negative x minus 7, which is just going to be negative 5x minus 7. So if that's your original function, here's the equation for a horizontal reflection first. Okay? So far, so good? So let's call that f of x. So g of x is my original. F of x is going to be the image of that after a horizontal reflection. And actually, just because it's good to look at, I'm going to type in that original, 5x minus 7. You don't need to do this, just watch. And I'm going to type in what supposedly is supposed to look like a reflection horizontally. And you tell me if you see it. There's your original. There's your reflection horizontally. Does that look like it reflected it horizontally? Yeah. Okay. Now, I'm going to pick up where we left off with the f of x function. If I want to flip something vertically, what do I do to this? You make it a negative out in front, exactly. So you make it negative f of x, which really you're just going to take your negative 5x minus 7, and it's a binomial, so lock it up in parentheses, and we're going to negate that out in front. And when you do that, it's going to bring us to positive 5x plus 7. So I'm going to go back to my graph just to show you visually. I'm going to get rid of the original because now I'm picking up where I just left off, and I'll compare that with 5x plus 7, and you tell me and verify for me that it did in fact flip it vertically this time. Does everyone see that? So now it's symmetrical to the x-axis. Okay? So you should expect to have to kind of rewrite a new equation after a transformation has taken place. Good, good? Any questions? All right, so next one, same skill. We have a random parabola equation. It wants us to rewrite it after a reflection in the x-axis. Let's quick think about this. If you're flipping over the x-axis, are you flipping horizontally or vertically? Vertically. So does the negative go inside or outside? Outside. So we're going to write an equation for negative f of x. And again, because f of x was a trinomial, I'm going to lock it up in parentheses and throw that negative out in front. And then to get to my answer, I'll just distribute that. Negative 2x squared plus 3x minus 8. Option 2. And again, I could graph that parabola for you and graph that parabola for you, and you would verify that it did flip over. Let me ask you this. What do you guys know about a parabola in the direction it opens if it's y equals a positive x squared versus if it's y equals a negative x squared? Yep.
Doesn't the positive one face up and the negative one face down?
Very good. Opens up, opens down. I know you guys already know that. That is the way it is because of transformations. So if you look at this function, 2x squared, that would have opened up. We flipped it vertically. Now it opens down. On the other side, think about this. Y equals x squared. We know that opens up. What if I negate it within the function? If you negate it within the function, it's supposed to flip it horizontally, correct? When you simplify that, what do you get? Still a positive x squared. So, and this kind of relates to the question you asked on the homework. Because when you take a parabola, parent graph, that's not very symmetrical. There's the parent graph. And you flip it horizontally, it's going to land on top of itself. And you can see when you do the flipping and rewrite the equation after a horizontal flip, it's still going to be itself, which is just kind of neat. Okie doke? All right, after a reflection in the y-axis, so a y-axis reflection, here's your y-axis, we're going across the y-axis. That's a horizontal, so we want to negate it within the function. And this is different, because if you're doing it within the function, you actually have to plug it in. So 4, and I'm going to replace all my x's with negative x. And the thing about a negative x, when you square it, it's going to be positive again, so that's just going to turn into 4x squared. This one is going to change to plus 7x, and then the 2 is obviously unaffected. That is option. See how close they all are? There's no guessing here, because they all look pretty much the same. They just mess with the signs. I'm going to skip 5 for now. It's pretty straightforward. Okay, exercise 1 here gives us a function, asks us to rewrite a g of x equation if g of x is 2 times f of x. First of all, it doesn't ask us this, but I'm going to ask you, what transformation takes place? Of which direction? Vertical stretch by 2. Very good. The 2 is outside. It's a multiplier, so there's your stretch or compression. And because it's 2 and outside, it's vertical. So very good. So if you want to rewrite this, again, when things happen out in front, I'm literally just going to take this and do double f of x, which means I'm going to double the equation. When it's vertical, you're kind of doing something outside of the function, and then you have to just simplify, versus you saw when it's horizontal, you're actually plugging something in. There's your equation. 2x squared minus 8x minus 10. That's your g of x. Exercise 2. I don't think I have time to teach you about the minimum feature. Some of you may know it, but we'll get to that on a different day. They're giving you a point on the original graph. Which of the following points must lie on the graph of 3 times f of x? So, who haven't I heard from yet today? Corey. What transformation did they apply?
Vertical stretch,
By
3.
3. So which coordinate does a vertical movement affect?
The y coordinate.
The y. And it's stretching it by 3. It's a multiplier, right? So 12 is going to become 36. There you go. The x coordinate does not change. It's negative 3, 36. Awesome. And lastly, back to our turning point. We have a function, and then we have a new function. What is the transformation on this new function, Jason?
Yeah, horizontal.
Horizontal.
Stretch.
It's actually compression because horizontal messes with us, right? Compressed by a fourth. We would reciprocate that. Does that make sense?
Yeah.
So which coordinate is that affecting if it's horizontal? The x. And so we need to just squeeze that in by a fourth. So what's that divided by fourth? Negative 3. Negative 3/8 is your answer. Okay, so there was that whole other layer to transformations that kind of kicks it up a notch. So you see why we spent a second day. Would you do the honors and give everyone one of those, please? Thank you, Alexa.